So, it's very pleased to introduce Mr. Temkin from Hebrew University and Institute, who will tell us about resolution of singularity. I forgot the full title, but that was the subtitle.
Sort of, yeah. I think I announced new method, but mainly will be occupied probably with old method and new method and a bit. Yeah. But the presentation of old method probably is adopted to be easily modified for new ones. Yeah. So thank you very much for giving me into the talk. Yeah. So let's say resolution of singularities in characteristic zero. So this will be blind assumption from the talk. Let's start with introduction. So the goal of this thing is to start with a singular variety or scheme or analytic space, whatever, geometric object, which is close enough to algebraic varieties, not any geometric object, and X, and find a resolution of singularities or desingularization, which is a cover X resolved to X, so that this guy is smooth or non-singular. And what means cover? Well, we can argue and maybe find a compromise, but in case of characteristic zero, we know how to do best possible. So actually, one always wants this guy to be proper. Let's see, F is proper and birational. Proper, well, yeah, since this is colloquium talk, I'm not assuming much algebraic geometry or scheme theory, and at least I'm trying to pretend that you can think complex analytically. So if you wish, think complex analytically, proper just means compact. Okay, in that sense, compact map. Birational means generically isomorphic. Okay. Now, and in addition, again, in characteristic zero, and maybe not since Hironaka, but after him, it was discovered when one can also make this canonical or smooth functorial. Which means that for any smooth y to x, the resolutions should be compatible. So we don't only solve a single resolution problem, we solve simultaneously all of them. And this is very beneficial because in such a case, this is automatically equivalent with respect to any smooth group action. And this is compatible with open immersions. Open immersion is a smooth morphism. So actually you can solve your problem locally and it will agree on intersections. You can globalize for free. So if you are going to prove smooth functorial method, you can work locally. You should check functoriality locally, but you can forget about any global setting. And this is very beneficial. It simplifies your arguments a lot. Yeah, you prove stronger thing, it simplifies. Now, the notion is due to Wlodarczyk, as I'll soon say, and it's about 2003. Before that, people talked about canonical without making this precise, but yeah. Again, I'll tell 2 words about story soon. Okay, so in our talk, everything will be smooth functorial, and we'll always talk about local methods because actually we are constructing something which is enough to construct locally. Now, one more remark. As I said, this makes sense for algebraic varieties, schemes, excellent or quasi-excellent, but quite general or formal schemes, again, with some excellent assumptions. Complex analytic spaces, or maybe non-Archimedean or rigid spaces, and so on. Originally, proofs had to deal separately with different cases, and Hironaka wrote a separate paper about complex analytic case with a lot of new ideas. Afterward, when people discovered canonical method, it was clear that canonical works with same in all categories, but formally you have to rewrite everything. Of course, nobody did it, they just claimed everything works, but okay. But now there is a formal implication. If you really do this case strongly enough, and not only smooth functorial, but so-called regular functorial, sort of smooth morphisms, which are not necessarily of finite type. For example, formal completion. If you are able to do it functorially with respect to a strong thing, you'll glue automatically also for complex analytic and whatever. So the question, in fact, is algebraic. If you get a strong algebraic solution, all the rest follows formally. But on this talk, this is sort of expert mode on a remark, now expert mode off, so you can just think about complex analytic throughout the thing. Okay? Good. Now maybe 2 words about history. So I wrote it here to steal 2 minutes. So the classical question which is presented here, and it works with in all these settings. Maybe we should take it back to Zariski. In 42, Zariski resolved free falls. So he proved in characteristic 0 resolution of dimension 3. It was major breakthrough. It took 22 years to get after that, and when a student of Zariski, Hironaka, proved resolution in all dimensions in characteristic 0. Now Hironaka's proof made a lot of new, it contained a lot of new ideas, and in particular, he not only worked with varieties, he worked with some formal completion, so he had to, already Hironaka had to work more. Now, Hironaka's proof was extremely complicated, and it contained much more ideas than needed. So afterward, in a sense, a development, about 30 years, many people, including Hironaka himself, tried to cut off pieces which are not needed and converge to minimal algorithm which is self-supporting by induction. So what you need for induction, what can be omitted, what is the minimal algorithm. And it took a lot of time by Giraud, Hironaka in 70s, Bierce, Milman, Villamayor in 90s. First time they found some canonical method or algorithmic method. This is time to say that Hironaka's proof was existential. He did not construct any algorithm. It was not possible to give it to computer. It only proved that it exists. And this is one of the reasons why it was so complicated. And explicit algorithm started from Bierce, Milman, Villamayor in 90s. And then Wlodarczyk formulated that actually you have stronger property, better to work with, and now this is the golden standard. In 2006, Kolar wrote a book, so it was graduate course. So this converged from Fields Medal to graduate course on master level, where during semester you can teach this. But nowadays, probably even half semester would be. Okay, and for a long period, many people worked and discovered different descriptions, and all of them were the same method. So, yeah.
In Johanna 2 is more, like removing indeterminacy of Mach or for embedded varieties?
We'll talk, of course, about embedded and so on, about principalization. Yeah, it will be, yeah. Next part. But I just want to give broad picture and then we'll converge to classical. So for long period, it was the same method. So many people described, they pretended, by the way, Villemayor and Buster-Millman pretended not to understand method one of another, but the method was the same. Yeah, they did not understand the proof, but the algorithm was actually almost the same, yeah, except some idle operations maybe, but yeah, small combinatorial details. And the question was, is it a matter of life that we have just one method, or everything was just based on Hironaka's ideas, and that's the reason? And it was very unclear. And only in 17, with Abramovich and Wlodarczyk, we discovered a new method, just really new method, which works with logarithmic varieties. And in the end, it also resolves morphisms. So it gives you semi-stable reduction or something in families. And it was sort of a new method with new tools, but something similar, something new. And after that, in 19, another generation of methods, so-called weighted to dream, was discovered independently by us and by McQuillan. And here stacks or orbifolds are used quite a bit. And there is a combination, logarithmic with stacks, and now the very recent in 25 with Belotto, we also established foliated resolution of on foliated things. So most probably will not come to this. My goal for the talk is to describe the classical method, and then a bit about weighted and dream methods in last 10 minutes or whatever. But foliated most probably will not get to it today. Okay, so that's all about history. And now I want to start with the embedded method. Yeah, so embedded resolution principalization. So in first approximation, one after Hironaka says that the resolution is embedded. This is imprecise. I'll try to argue why this is a bad notion, but this is standard terminology. At least it was standard terminology. And it says as following. Let's embed locally. Embed Z you're working with. Let me write here maybe Z from now on. Okay. Singular guy will be Z into a smooth one. We'll call it manifold or ambient manifold to stress that this is smooth and it contains what we want to work with. And imagine, of course, this is only locally, but we don't care. Yeah, we have all the reasons to work with. Now, again, expert mode on. If you work with stacks or whatever, it locally you still can embed, and you don't care because you have smooth controllability. Okay. Good. So, and then work with X. So let's find a sequence of simple modifications so that our Z is embedded here, and then there is some Z1 which is embedded here. And this guy is smooth, and all Xi is smooth. And these things will be what we call smooth blowups. I'll immediately come to definition. So the idea is that we embed into something smooth. We keep smoothness of the ambient thing. And inside these things happen with our Z, and in the end we get to something smooth. But we try to improve it by working in nice neighborhood, a nice township. Okay, good. Now, example. So let's take a surface with coordinate x, y. Let's consider graph of a function z equal x over y. Yeah. So all lines which pass through the origin now separate on such a graph. So what we get here will look like something. And there is a whole line which is mapped now to the z-axis, which is mapped to the origin. So this is the standard description of y chart of the blow-up of, well, let's denote this guy A2, or let's denote it X, of X at the origin. Yeah, so we'll denote it blow-up of X at the origin with y chart. Okay, in fact, everybody who teaches calculus, calculus 2 about lack of limit, if you have limit along any line, but not global, this is the best possible example. An absolutely classical situation. Now, already this construction allows you to resolve some singularities. Also, yeah, I forgot to give you a couple of examples of singularities, but okay, so we will do it now. So, you can consider such a thing. Yeah, example of resolution. Okay. And of course, just separate 2 points, 2 branches. Of course, such a thing can be realized as embedded. We can do it in the plane here, and when 2 tangents are separated, and we realize them, and the exception line is here. We separate 2 points. You can consider, for example, this thing. T squared T cubed projection onto YZ plane. We forget about T, we get something singular. Yeah, and when we separate it, we'll touch the exception. We can consider something like cone x squared plus y squared equal 1 resolved to a cylinder x squared minus z squared. And here we'll have x prime squared plus y prime squared minus 1 equals 0 or equal 1. And in this case, the exceptional sits inside our transform of z. So the exceptional sits inside z itself. Good. Now, a couple of general words about the blowing up. So in general, if local coordinates on x are t1 up to td, and v is smooth inside x, is given by vanishing of t1 up to tr, then blowing up of x along v is union of R charts by TIs, and on ice chart, coordinates on ice chart are T1 prime, which is T1 over Ti. Ti is unchanged, Tr over Ti, and the other variables are unchanged. We don't do anything starting from R plus 1. So these are the new coordinates. Now, once we have this, and what you actually do, you inside of x, here we have v, and over v, we insert projective normal bundle of V inside X. So we replace V with all directions outside of V. In this case, we just replace with P1. In case of a point in dimension n with Pn minus 1, and in case of blowing up something of larger dimension with some family of Pns. Okay, good. Now, what is important also to stress is that the pullback, let's denote this F, pullback of V is given just by on I chart is just given by vanishing of Ti. Because on the pullback, I divided all generators of ideal by, now we are divisible by Ti. So the pullback of ideal is now becomes principal. And in fact, maybe we'll erase these. Okay. And in fact, for any ideal I, ideal on X, there exists a universal modification, let's say non-zero, X prime to X, which is denoted blow up of X and I, such that the pullback of I, by which I just denote I times O X prime, just the ideal generated by the same functions as I, but on the pullback. Yeah, in this case, the ideal was generated by T1 TR, so pullback generated by T1 up to TR still. So this guy is invertible. It is locally generated by a single not zero device. Okay, so such a construction, I gave you example when it exists for blowing up a smooth center with same formulas. This is an excellent property of algebraic geometry. In many cases, your formulas, algebraic, they are not sensitive to smooth or not smooth. You can substitute whatever you want. You can substitute the same construction, which is described here. Once you discover the formal with Proch, and it will work very ideal. It will give you universe. But in this case, the outcome is smooth. It's visibly smooth. And in general case, it's very far from being smooth. You can blow up general ideal. You'll get something complicated. I'll give you just one example, which will be important later. Blow up of A2 along X y square is actually a orbital. So let's say this is X, and this is X prime, and you should take X or Y chart. Y square over X, yeah, X chart. You'll get Z equal Y square over X, and three coordinates are related by X, Z equal Y square. So you get something singular. You start with something smooth, you get something singular. So there are a lot of blowings up. A general ideology, which I'll try to argue in the sequel, is that you should use as much tools, as many tools as possible. So you would like to blow up whatever you want, but you have also to stay smooth. Yeah, and this is the limitation. And because of this, in classical situation, people only blow up classical things, because anything else, you don't have any reason to get, even in simplest case. Okay? And now let's consider one more example. Before we go to description of the classical method, let's see one more limitation of the method. Because in principle, what we saw here, in all three cases, was the following. We embed our singular thing into smooth one. We take the singular locus, we blow it up, and we improve the singularity. So now let's consider the situation when it won't. Okay. Also very classical situation and very useful example. So let's take Whitney umbrella. So we take x, which is A3, okay, of characteristic 0, and we take here inside of this z, which is given by vanishing of a function x squared minus, let's see, plus y squared z. Let's try to draw a picture. Looks something like this. Okay, I guess Luca Lusin insists to finish in this way. Now this point is pinched. It is visibly worse than everything else. This locus C is self-intersection or SNC locus. C without zero. SNC locus, not SNC normal crossing, sorry, normal crossing. So we have two branches which intersect. C is the singular locus of C. So we have one bad point, few points which are better, and all the rest is smooth. And of course, the natural guess is take this guy and blow it up, and when we take x prime, it will blow up of x. And let's take the z chart. This is the interesting chart in this case. And what we'll get after we have new coordinates. X prime is x over z, y prime is y over z, and the pullback of z will look as follows. We should substitute this here, and y prime z here. We get z from z square, take it out, and we are stuck with the same times z squared. So this is vanishing locus of z squared times x prime square plus y prime square. Okay, so we get twice exceptional divisor, twice because the order was actually 2, and we are stuck. So the real algorithm works as follows, as a human would work. You try this, you blow it up, and you see that it does not improve, and after some collecting some memory, and in fact it blows it up once, but this requires a computation with concrete algorithm to understand that it won't work, and then it blows up the whole line, and this improves. Yeah, but I don't have time, but there is a very simple argument which says that even more is true. You can take any modification just at the origin, but you won't be able to, it won't improve the singularity. Pitch point will reappear, even if not just blow up of simple point, but any nilpotent structure you can put inside, it won't improve. And the reason is that, okay, just to worse, expert mode on, your normalization, if you take normalization of Z, when C is covered by twofold cover, but which is branching over O. And this branching point can go nowhere, whatever you do westward. And that's also the idea of how that you can construct even wilder examples in characteristic 2, but this is out. Okay, so now let's return to. One has to design a complicated algorithm. One cannot hope just to give invariant and improve it each time by once. There must be some memory in the algorithm. Okay, and now last remark, which I promised we should actually about principalization. So before I go to the classical method, so So work with I, which is the ideal of Z inside X, instead of Z itself. This is natural, as I explained, algebraic. It's easier to work algebraically. We embed everything in smooth thing. We have good coordinates all the time. So we prefer to work algebraically. And moreover, Hironaka says that on each blow up of say X prime, which is blow up of X along J, worry that the ideal we work with is contained in G to some power D. It means actually, morally, yeah, let's say that this is blow up of X along V. This means that D copies of V is contained inside Z. This is the minimum. Okay, first thing. And second, for some D, we'll immediately, okay, we'll soon discuss what D is. In this case, for example, D equal 2. The order was 2, and we got twice exception. And if we insist on this, then after blow up, let's see what we get. We have I times OX prime, pullback of I, okay? And it contains, it's contained in pullback of J to the D, which will be ideal of exceptional divisor to the power D. The pullback of J is exceptional divisor, as I explained. Pullback is compatible, of course, with product of ideals with powers. So it will be this. And because of this, we can define set I prime, pullback of I, divided by exceptional to the power minus. So this makes sense. This is possible. Okay? And Hironaka says the following. So find a sequence of such transforms so that I n plus 1 is trivial. Let me just refine the picture you already had. So Hironaka says that instead of working with this, let's forget for one moment. We'll work here with, okay, maybe I'll write Vi0, which is original Z. And then we have Vi1, which is something strange. We just defined it algebraically. And honestly, it can contain exceptional components. It does not have to be even irreducible. It can be complicated. We have no control. We only work algebraically. VIN. And then here we want to have something else.
Sorry, what is I1?
I1, it will be transformed. It will be I1 will be transformed. If this is F1, it will be F1 transform of I0.
Ah, okay.
Divided by.
Oh, I see. It's what you call I prime over there.
Huh?
Okay, so I prime over there.
It was, yeah. For X prime, I write I prime. For X1, transform will be I1, okay? And the last transform is empty. Now, inside of this guy, we have Z0, which was just the same. Z1 will be inside this, but maybe not equal. And the miracle is that here will miracle. But at the one step before the last one, we'll get smooth Zn, and it will be also equal. It will be also equal to n's to v. Yeah, so we blow up centers v0, v1, and so on. And the only way to get something empty is to blow up the whole guy. At this stage, the guy is smooth. And that's the reason that it must coincide with strict transform.
All the centers are smooth.
Yes, all centers are smooth, yeah. Now, as I formulated here, and as always people formulate, it sounds like just a coincidence, a miracle, whatever. You have two completely different problems. You insist to resolve ideal by smooth blowups, and somehow it also your two resolutions separate in the middle, and they meet towards there. Yeah, I don't have a two conceptual argument, but I can give you semi-conceptual argument why principalization is a problem from the same set. Okay. Again, maybe a bit expert mode on, but yeah, just for 1 minute. So the point is as follows: amount of general blowing up of ideals is huge. These are where by Chow lemma, by simple result in variational geometry, they are cofinal among all modifications. And moreover, in Harston there is an exercise that if you have projective modification of projective variety, then it is a blow up of something. So almost everything is blowing up. What we really construct here by this operation, I claim that if I take f from, let's say, h from xn plus 1 to x, then pull back of my original I factors as pullback of zero center, maybe to some power d, times pullback of first center, and so on. So morally, what I'm doing, I start with any I, and I factor it to ideals of exceptional divisors, which I blow up at each stage. Okay, so for this reason, by universal property of blowing up, I got a modification which is refinement of blowing up of I. So such blows ups are cofinal. So the real meaning of principalization is that for any modification of x, I can find a final modification which is obtained by very controlled operation, by keeping me smooth all the time. And the miracle is that the claim that smooth modifications are cofinal is stronger than the claim that in any variation class, smooth models are cofinal in lower dimension. Okay, but at least it looks natural that two questions are related. Okay, good. Now let's return to concrete description. So I want to show how Hironaka actually achieves, or maybe not Hironaka, maybe his followers, how current methods achieve resolution. So classical math. Okay, so first of all, primary invariant. It has a most important invariant of the resolution to any ideal I on a smooth variety X. I want to assign some number which measures how bad it is, and it is called order of I on X, and it is defined as maybe I'll write it. of I. This is defined as minimal number D such that dx of I less or equal D equals to OX. Now, by dx, we'll denote derivations on x. Derivation of I, or let's say of ideal generated by one at n, is by definition ideal generated by the same things, and d over dxi of fg. Okay. Ideal generated by all derivations and all elements. Now, such a operation locally at a point reduces my order by one. Yeah, for example, maybe I'll give example. It's faster than do anything else. Order at 0 of something like t cubed x squared plus y, or zx squared plus y cubed equals 3. And when I derive it once, the order becomes 2. When I derive it d, I get to a unit. So ideal is clear. Okay? This is the meaning of this invariant. Now, 2, we blow up V such that IV to the D contains I. Okay, let's denote this guy J. So, maybe I'll just remark that blow up of V, which is also blow just by definition, blow up of the ideal of V, it equals to blow up of this power. Yeah, a very simple computation shows that if you want to make ideal invertible, it's equivalent to making its power invertible. So classically, of course, people only discuss blowing up smooth ideals. I claim that on the level of morphism, it's the same. On the level of transform, yeah, I don't have to worry for D. And also conceptually, it's more correct. Really, we blow up this power. But geometrically, it just means that V lies inside D order locus. So we say that primary invariant of our ideal is the order D, and we only want to blow up centers which improve the primary invariant. So we only blow up inside this order D. This is actually what is playing. And what I'll do, I'll transform all time by D. If I blow up inside order D, like our example here, exception will show up in power D, so I can always remove this power. Good. Then 3. Take any coordinate T. Coordinate means order equal 1. Inside derivation D minus 1 of I. So this is local construction. I'll write locally. At any point where the order is D, after deriving D minus 1 time, I get to ideal of order 1. So there is an element of order 1. Now, this element defines a hyperplane. I'll denote VT, and both element and H are called maximal content. So you should think about this as hyperplane, which has maximal contact with singularity. It's best possible approximation of singularity with something smooth. Okay? This, of course, doesn't work at all in characteristic. So this breaks completely. Okay. maybe I should say maximal contact is due to zero. This was contribution of zero in symmetry. Then the next thing is that define coefficient ideal. C of I as the sum of all derivations from 0 to d minus 1, all non-trivial derivations. But we want to take weighted sum. The reason is that the order of zeroth derivation is d. The order of next derivation is d minus 1. The order of d minus first derivation is 1. We want to rescale them accordingly, so we take here d factorial divided by d minus 1. In order to put them at the same level of the same weight. Okay? So this d factorial is responsible for horrible complexity of it. You can put here LCM of 1 up to 2d, but this won't improve much. Good, and then now the last thing, the point. Order reduction or d-order reduction of I on X is equivalent to d factorial order reduction of H, maximal contact, and coefficient ideal restricted to H. And the switch from d to d factorial is because of normalization I had to impose. Now this looks like complete comment of nowhere, but I'll try in 4 minutes to give you example which should convince you with why this works. But the point is that actually we take our principalization question, which we try to resolve by reducing the order from d to d minus 1 and then d minus 2 and so on. And the stage of reducing d by 1 is actually equivalent to solving another problem, a problem about much more complicated ideal, but in dimension 1 less. So if this is possible, we get induction on dimension and we will. Okay, now example why this actually works. So let's take local coordinates T1 up to Td, and T is T1. And I can arrange, and let's take I generated just by a singularity. And honestly, before Hironaka, people always try to resolve only hypersurface because this is enough to resolve singularities actually. And Hironaka recognized that for order of, if we start with I, coefficient ideal won't be generated by single elements. So for induction reason, he switched to general ideals. So, but let's here take just F. And then you can actually, without loss of generality, you can arrange your coordinates. So whatever will look like Td plus A2 Td minus 2 plus AD, where each AI depends only on other coordinates. Yeah, so you take your presentation, you start to make linear changes of variables, and you easily, relatively, here maybe will be some unit which you can then get rid of. I skip details, but this is really without loss of generality. Okay, and in such case, what is CI? CI is generated by d to the power CI on H. When I restrict to H, I keep only the guy which is without T's. So when I restrict zeroth derivation, I get a D. Okay, when I restrict first derivation, I get A1. So it will be A1 to power d factorial over 2, and so on. Okay? And now exercise. Check that the order of S of I equal D if and only if the order x lies in H, which is vanishing locus of T, and the order of C of I on H at point X is larger or equal to D factorial. So the order of this guy is D if and only if the order of this guy is at least 2, the order of this guy is at least D, and so on. Okay, so the order of the whole polynomial can be encoded by order of coefficients. And the trick of Hironaka was to separate to a question about T and question about coefficients. That's actually, that's all what's going on in the method. Of course, I claim here my stronger claim. I claim that the order will persist to be compatible after blowing up, which respect the structure, la la la. Okay, everything is under the rug. There is something to do, but this is convincing that you have good chance to. And nothing like this exists in characteristic P. You cannot start just no. Of course, no start. Okay. So in 2 words, this is the real miracle or machine of Hironaka, and all the rest is technical issues. Okay, and maybe last point, why I don't have here A1. Why? Of course, I can get rid of A1, but the reason is that if I would have A1, after deriving D minus 1 time, I would get D factorial T plus A1 times something. So maximal contact would not be T, it would be T plus A1. So I just changed coordinates so to get maximal contact, so this is A1. Yeah, so, and that's it. Good.
In Hironaka, there is always this full story of normal flatness.
It's completely not needed. Okay, well, we can discuss later, but the minimal thing which is inside there is called now called weak resolution. Okay, maybe I say it in one word. The resolution which we get in the end by restricting our method to this is not obtained by blowing up smooth centers in this. It's obtained by blowing up restriction of centers here to this. So if you restrict transforms, you blow up something complicated. And Hironaka wanted to blow up only smooth centers inside your thing, and this requires much more work and normal flatness in order to intersect that smooth thing. But this thing in the end, it's not needed for simplest approach. Okay, good. And maybe I'll just say in words, I'll not write on the board. There is just one complication in this method, and complication is written here. It can happen that you start with something of order D, let's say T squared plus X cubed plus Y4. And if you apply such construction, your order will be above D factorial. So you encode the problem about reducing the order below D factorial, but the order of this guy is larger. So when we'll try to do the same thing on H, we'll not do good transform of ideal. Exceptional power will be collected. So you can say it's not big deal, and then we'll remove it by hand, but this forces you to respect the exceptional. And this forced Hironaka to add simple normal crossing divide, to request that exceptional simple normal crossing. So morally, he added log structure to all the business. And when you can only blow up so that you are transversal or have simple normal crossing with exceptional, because you must also keep your exceptional simple normal crossing throughout your process. This restricts your amount of centers, and you must add some extra stages to respect your exception. That's actually what's going on. But it's not important for what I'm going to tell in 5 minutes. Okay. Okay. Yeah, so now let's discuss the new methods. So the logarithmic one I will not be able to discuss. It needs more technicalities, but morally, if you know well enough logarithmic geometry, you take what I wrote here and put log. Instead of derivations, you take log derivations. This gives you different order, log order, and most of construction works throughout. At least half of thing just will work. Yeah. Now, but I'll discuss weighted. So fact. So I claim here that this blow up is bad, but it can be made good. The fact is that there exists an orbifold refinement of blowing up of x at j, which is t1 to d1, tm to dm. And let me always assume that d1 is less or equal to d2, less or equal to dm. We will always order our centers in this way. So one takes now centers with weights, and there is stack-theoretic refinement of this, which is smooth. I'll denote it stack-theoretic blow-up. This is imprecise, but just as a first approximation of how you achieve such a thing. So idea. And it's really imprecise. Blow-up will take y equal to x of t1 to the power 1 over n, 1 over 1 over, let's say, w1 and 1 over wn, and such that d1 w1 equal d2 w2 and so on. And when blow up y at such a center, and then divide back by the cover. So you'll get y2x is some g cover. You blow up y by some power of maximal ideal. You get something smooth when divide back, but stay in orbifold. Okay, anyway, let's ignore. Just take as a black box. There is a way to refine this blow up to a smooth stack, so this guy will be coarse modulus based.
So what you blow is this T1, D1, Tn, Dn.
I blow up this ideal, yeah. I blow up this ideal, but there is a refinement. There is a stack-theoretic version to refine. Of course, in the case which is written here, you'll get orbifold structure of plane divided by Newton.
This is some canonical structure, or you need to pick some data?
It's canonical. It's absolutely canonical. And then we study also how much you can change coordinates here afterward. Yeah, it's canonical. But this construction is it's only idea. It's not. There is some, okay. In one word, you can write down some approach construction, but your graded thing will not be generated in degree 1. When you divide by j and divide by as a stack, and you really get stabilizers because it's not generated in degree 1. Okay, that's it. Yeah, but yeah, I have just 2 minutes or 3 minutes, maybe I started 2 minutes late to formulate my theorem. So here, using this extended pool of basic modifications. So ATW and McQuillan. So it says that for any ideal I on X, let's say non-zero, there exists unique J containing I such that locally J is of this form, T1, D1, and then. And honestly, this can be even rational and not integral, but again, that's ignore technical issues. Such that this D1 up to Dn is maximal possible. In the Lex order. So I claim, with unlike the situation earlier, there is one canonical largest possible set. Okay, with largest possible degrees. So sort of maximal tubular approximation of UI, maximal tube which is contained inside. And when we just by definition so set the multi-order of I, not just order, but multi-order equal to this number D. D1 up to D. Okay? So this is first claim. And then second, of course, you can ask, and what happens if I blow it up? Because now I'm allowed to blow up this thing and stay smooth. I just move to the world of stacks. And then the claim is that if you take blow up of I at J, of X at J, but blow up as a stack, we take I prime equal to I full back time divided by J, then the order of I prime will be strictly smaller than the order of I. And that's it. This gives you resolution without any memory, without anything. If you're able to prove this, then you get just canonical algorithm. So locally you are more complicated, you use more tools. You resolve only a stack. So if you want to get variety in the end, you'll have somehow to get rid of stabilizers. But this is combinatorial and relatively simple procedure characteristic zero. So it's not an issue. It was known well how to do this. And you get canonical resolution without anything. Now, we last just a minute. Yeah, now extra time, but yeah, just 1 minute. You can ask, and what happens in the case of Whitney umbrella, where I claim that you cannot just modify this point and improve. And the reason is that in category of schemes, you are not able. But here, okay, I don't have time to compute, but see, very simple computation shows you really, but you get simple normal crossing along the line. Why this happens? Because instead of pitch point, you will put here something with mu2 stabilizer. And this is precisely the quotient of this normalization curve by mu2, but when you remember the stabilizer. With this stabilizer, it becomes normal crossing along the whole line. So this proof that everything is impossible for varieties is just completely disappears in world of stacks. So yeah, thank you very much.
Questions?
Can you at least give the statement for foliations?
Foliations?
Or is it?
No, I can. But it means that we don't get resolution for foliations. Also, one should decide how much it's possible, but we say that if you have X, which is foliated, yeah, so you have some F inside
So X is smooth. X is
smooth. Smooth, yeah. Again, ambient space with foliation. Yeah, ambient with foliation. And you have some idea of I in OX. When there is this principalization, again, and we believe that classical does not exist for foliations. It's too complicated problem to support. There exists a principalization of I such that X prime to X, this guy is mildly singular. You cannot, when you start to blow up foliation, you are unable to keep it completely smooth. You'll get some logarithmic, simplest logarithmic singularities. Morally, you blow up, so with centers which we blow up will look like T1, D1, Tn, Dn. And when U1, E1, UM, EM, these guys are increasing, these guys are increasing, but there is no relation between the two. These guys have f order 1. You degree, they are transversal to foliation. These guys are f invariant, or f order infinity. And the total invariant in this case should be d, and then infinity plus. Okay, and morally you work now with two things. You work with f as much as you can. When it becomes infinite, you stabilize with f, you get f invariant thing, and you work with d. So this is the moral of this in 2 words. But without stacks, just it seems just it was impossible.
It is blowing up of d1, dn, dn. Is it the di and a flag which matters? Or
Okay. Really, you have a monomial valuation with on T1, Tn with these things, and the change of variables which is allowed is that if all these are different, then you'll have something invertible here, anything here, and some like intersection of GL and O, and it's conjugate by T1 to some power T2, and yeah. So sort of such structure. Moreover, in variational geometry of such things, you see structures similar to Bratty's buildings, and it's sort of local analog of Bratty's buildings, and yeah, but it's completely not explored. I mean, these are observations, but we have some plan with to do some part of it, but it's very new. I mean, it's not unexplored so far. Yeah.
but you have to tell something precise to tell that you have a unique things which
I say that it's just this J is unique for maximal lexicographical order. And one more thing, and has maximal possible support. Okay? I mean, if you have few components, you must take all components. But that's it. Just you have just one maximal thing. So I know if you take just example, if you take T1, G1 plus T and the end, then it will be of course T1 to T1, T2. And it will be independent of anything.
Thank you.